Hello, students. This is Mr. Ezra. I am so sorry that I am not at school today to talk about statistics with you in person. So I decided to record you this video just so that we could continue our conversation. Remember, we are building towards a test next week on Thursday. So make sure that over the weekend and into the early part of next week that you're finishing up any questions from the textbook that have been assigned and that you're working through the rest of the practice problems in your packet. Everything should be ready to go by Thursday. In class, we ended, depending on which period you have me, either into this problem or just starting this problem. So you might have a little bit of review here at the beginning, but we're going to just cover this example and the matched pairs example as quick as I can in the video today. So this question goes back to the children's game Don't Break the Ice, and I don't know if you've never played this game, but you should have because it is awesome. And I encourage you to pause the video. You're already on YouTube. Do a search at the top for Don't Break the Ice and see this game played in action. It's amazing. You will want to play. But the basic premise is there's these little blocks of ice. They're plastic, but they're pretending to be ice, and they're all kind of stacked in this board. And you hit the ice out with a little mallet, one ice cube at a time. You take turns, and if you knock out more than that one ice cube, like if the whole thing comes crashing down, then you've just lost. So you want to tap out one cube without disrupting the other cubes that are there. Um, for this game to work, the cubes have to be 29.5 millimeters wide. Now, there can be a little variability around that, but there can't be a lot of variability around that because if it's much more than 29.5 millimeters or much less than 29.5 millimeters, either the pieces will fall out too easily or they'll be so kind of jammed in together that the game becomes very difficult. So you want these cubes to come out of the machine formed in the right way with the right specifications. To ensure that the machine is working well, a supervisor inspects a random sample of 50 cubes every hour and measures the width. We're going to use the information from our printout here to test the claim, and we're also going to verify this claim with a 95% confidence interval. So there is some information that we want to highlight as we're working through this problem, and we are also given a little bit of a computer printout here. So we see the test of mu versus not mu of 29.5. So we're actually given our hypotheses here. We're also given sample size, mean, standard deviation. These three things here refer to the sample, the mean and standard deviation of the sample. Standard error of the mean would be the standard deviation or the standard error of the sampling distribution. So we could use this, we may not use this depending on which method we use to get our final answer. And then we've got a confidence interval. And before we do anything, I want you to think about this confidence interval and ask yourself, is the null hypothesized mean of 29.5 millimeters in this confidence interval? And if you look at the numbers here, 29.5 is in this confidence interval, and that means that it's a plausible truth for the mean. We don't know what exactly the truth is necessarily, but this 29.5 is plausible. It's in the interval. It could be true. And if that's the case, I can go ahead and tell you now that the decision when we finish this problem is going to be fail to reject the null. Because if it's plausible, if it's in the interval, then it's something that could be true. We don't have evidence that it's not true. But we're actually going to do the four-step process in order to answer this question. First, we want to tell what kind of test we're doing, list out our hypotheses, and define our parameter. So we've already been told what our hypotheses were, but if we weren't told what they are, we would have to use mu for the mean because we're talking about the population. 29.5 was what was given to be the length of the cube that's necessary. And we the game is going to be difficult if it's more than 29.5 or less than 29.5. So we don't have a direction. We've got what's called a two-tailed test here. Now, we must tell what the mean is, what this mu represents. It's the mean width in millimeters of the block of air quotes ice from this game. Now, we should always check conditions here. So we've got step 1 out of the way. Now we move on to step 2. Step 2 is checking conditions. The 3 conditions are the same conditions we've been talking about for weeks and weeks and weeks now. Was it stated to be a random sample? And yes, it was stated to be a random sample of 50 cubes. How do we check for independence? Well, it's the same check for independence that we have been using forever. We need a large enough population, at least 10 times our sample size. And this game has been very popular over the last 20 or 30 years. There have been tons of cubes of fake ice created for this game, certainly more than 500 cubes. So not only does this allow us to assume independence and proceed with the test, but it also allows us to use that sampling distribution formula for standard error or standard deviation of the sampling distribution. Our check for normality here, we have to do that 3-question check, where the first question we ask is, do we know if the population is normal? And no, we don't. The second question, is our sample size large? And this time it actually is. A sample size of 50 by the central limit theorem is understood to be a large sample because it's more than 30. And the central limit theorem guarantees that with large samples, our sampling distribution is going to be approximately normal. And in this case, that means that it's safe to use the t-distribution. After checking conditions, we do our calculations. Now, I, of course, in this answer put all the extra stuff. But when you're taking a test, like an AP test in a few months, remember, you must put in there somewhere what t equals. You must put in there somewhere what the p-value is. You must in there put the degrees of freedom. And it helps to have a sketch. All of that together is going to get you everything that you need. Now, if you want to add the extra layer of, I understand this really well and I deserve a 5 on my test, then you add in the formula filled in. You add in the probability statement using that t that you just found. And you realize that since this is a two-tailed test, you are going to have to multiply that probability of getting a t-score less than negative 0.9531. You're going to have to multiply that times 2 because the same exact area is going to be on the right side, even though it doesn't look like it in my drawing here. These areas would be identical because of the symmetry. It's also certainly possible that you just did the t-test in your calculator and you got all of this stuff that way as well. All right. If you're using the formula, remember the formula is, let's see if I can write it down here. T is equal to mean from the sample minus the null hypothesized mean divided by the standard deviation of the sampling distribution, which would be S divided by the square root of N. So something like that. That's what we have here. Now I got the 29.4874 and the 0.09347 from that table. That was the mean and standard deviation of the sample. It was given to us. Well, the real question we're asking here to get a p-value is what's the probability that we would get an outcome like 29.4874 or something more extreme? And in this case, we're looking at less than negative 0.9531 as a t-score and greater than positive 0.9531. We get a p-value of 0.3452. And when you look at this p-value and you think of it as a probability, you should think, well, that's not unlikely. I mean, that's very likely to be to get a sample like this. And since it's not unlikely, since it's not a low p-value, since it is greater than our alpha level, we fail to reject the null. Your conclusion should have a linkage between the p-value and the significance level, and a decision based on that linkage. So in this case, since our p-value of 0.3452 is greater than the alpha level of 0.05, we fail to reject the null hypothesis. That means that there is not statistically significant evidence that the mean width is not 29.5 millimeters. We don't have evidence that it is something else. So that means that the company seems to be producing ice cubes, fake ice cubes, that meet the specifications so that this game can continue to be enjoyed by people in the future. Also, let's link back to our confidence interval. We said this already, but let's remember that 29.5 was in the interval that was found by the statistical software package, that computer printout of statistics that we had at the beginning of the question. And since 29.5 is in the confidence interval, that's another reason that it is plausible that does not need to be rejected. There's no evidence. If it is a plausible truth for the mean, then we would not have evidence that that the true mean is something else. So we have to assume that it is 29.5. Our last example today is what we do when we have a matched pairs t-test for the mean. So remember, with matched pairs, this is a situation that happens when either the same person gets both treatments, or people are matched up, and because of similarities that they have in characteristics, similar characteristics, so they're matched up together. In this case, police trainers were seated in a darkened room facing a projector screen. 10 different license plates were projected on the screen, one at a time, for 5 seconds each, separated by 15-second intervals. After the last 15-second interval, the lights were turned on, and the police trainees were asked to write down as many of the 10 license plate numbers as possible in any order at all. A random sample of 15 trainees took the test and were given a week-long memory training course, and then they were retested. So the police academy would be interested to know if this memory technique is working. So they want to know, do we see improvement from the before training to the after training? This is matched pairs where each officer gets both treatments, and we're looking for growth. In order to do this, we're going to use a one sample test. So we're going to use the same t-test that we've used for the last few examples, but we have two samples here. We have the plates correctly identified, the number of plates correctly identified before training, and the number of plates correctly identified after training. Whenever you are doing this one sample technique for matched pairs, you always use the difference between the two treatments. So in this case, I'm going to subtract L2 minus L1 because a positive number is going to show growth. It's going to show that they did better after the training, and that's kind of what we want to know. So I took every single one of these outcomes for each officer after and subtracted the one before, and I put that in another list. Now, I don't have my calculator out to show you, but in your calculator, if you put all of these guys in list 1, and then all of these guys in list 2 exactly the way that they're written, you can arrow up to the top of the list and type in L2 minus L1, and it will automatically subtract all of these for you. Although with these numbers, it really wasn't that hard to say 6 minus 6 is 0, and 8 minus 5 is 3, and so forth. And what we see here is what we would expect to see, that the memory course seems to be working anecdotally because most of the officers did better. But we want to know, did they do enough better, significantly better, or better in a way where we would think that it wasn't just some weird random chance that gave us these outcomes, but instead something else like the memory technique working. So we're going to do a 5% alpha level matched pairs t-test to see if the course improved the memory of trainees. Is there evidence that the course is working? We start with our null and alternate hypotheses. I like to name the test that I'm going to be doing. That's always a good idea. But we certainly want to name the hypotheses and define our parameter. So a lot of times what you'll see here in situations like this with matched pairs is we use something called mu diff, which stands for the difference of the means. If the memory technique were not working, we would assume that the police officer would identify the same number of plates after the treatment as they did before. And if that was the case, if it was the same number, then we would expect the difference of means to be 0. Whenever you have matched pairs, I don't want to say every time, but almost every time, your null hypothesis is going to be that the mu diff is equal to 0. And for the alternate, you have to think, well, when I find this difference by subtracting the after minus the before, what am I looking for? To show growth, I would want a difference that is positive, which is greater than 0. It is okay to write this as mu after equals mu before, and the alternate as mu after greater than mu before. But we can't really put this in our calculator. There's no numbers here. So what we end up doing is subtracting the before to the left. Mu after minus mu before is 0, and that's what this is telling us here, that the difference is 0. Define mu diff as the mean difference in scores. Put what you're subtracting after minus before in identifying license plates. Okay. Checking conditions. We have a random sample of 15 trainees. Check. Good job. Independence can be assumed if there are more than 150 trainees in the population, and if this is a large city like New York City with police academies and stuff, there's very likely more than 150 trainees. To check normality, we go through those 3 questions because this is a means question, where we're looking at means, mean difference. So we ask ourselves, is the population known to be normal? And we don't know. Then we look for a large sample size, but this sample size is small. So we have to graph the differences, and you should have those differences in a list, and you're going to do a stat plot with that list and get something that looks like this. This is the box plot that I got. Now this box plot may indicate that there could be a little bit of skewness, but there's certainly not strong skewness, and there's no outliers. So it is safe to use the t-distribution. We can check off normality as well. For the calculations, again, degree of freedom you need to have. What t is equal to, you need to have. What the p-value is equal to, you need to have. Using the formula appropriately, filling in values gives you better evidence. Writing the probability statement and using TCDF gives you better evidence. But you can simply list t, p, value, and degrees of freedom and draw a sketch. And your calculator gives you all of these things if you're using the t-test in your calculator. Our p-value turned out to be pretty low. Definitely less than 0.05, less than the significant or alpha level that we set at the beginning. So since this p-value is low, we reject the null hypothesis. There is statistically significant evidence that the memory course improved the ability of trainees to correctly identify license plates. That's awesome. So maybe this police academy or this group should continue to use this memory course, and maybe Mr. Esra could get a hold of it because my memory is pretty horrible. Well, that is it. That's all of the notes, or at least all the examples that I'm going to show you for this chapter. The rest of the work is up to you. I will provide feedback. I'll give you some examples of how I've worked out things, but I want you to try the rest of the problems in this packet, and I want you to try the unanswered questions in the textbook that you haven't gotten to yet. And remember, it's important to read the text and not like word for word, but look through it. Make sure that you check out the examples. See if they've said something a little differently than I did that makes sense, or if there's something that you feel like you should add to your notes or to your understanding. I will be back on Monday, and so I'll either see you in on Monday or Tuesday, and we'll continue to prepare for our test then, and we'll take our test on Thursday. And gosh, we're wrapping up this course, aren't we? Um, I'm out of the classroom, out of town actually, but I will have my phone with me. So if you run into any questions after this video and you begin to work on um, your packet or your um, textbook work, or maybe you're working this weekend, feel free to text me questions through Remind, and I can't always answer them right away, but I do try to answer them as quickly as I can. All right, well, be good for the sub as you always are, and I'll see you next week.